Hi and Assalamualaikum. Welcome to our video presentation for PHY380. Our video is about the development of blade design for wind turbine power gen. Our team members consist of Putri Alisha Balkis, Putri Ilya Maisara binti Muhammad Helmi, Nurin Hanani binti Jasri, Nur Era Izlin binti Muhammad Amin, and Nur Hafizah Rafiq. Without further ado, let's get into the presentation.
So first, what is wind energy? So wind energy is actually a clean and sustainable energy where it has become an important source that transition to a low carbon energy for us to reduce our reliance on fossil fuels. Wind energy was captured by wind turbines, where wind turbines have evolved significantly over the decades as it has become one of the foremost cutting-edge technologies of renewable energy harvesting. In this video, we will be focusing on the wind turbine blades since it plays a crucial role in capturing wind energy and converting it into mechanical power, which is then transformed into electrical energy through a generator. The fundamental goal of a turbine blade was to extract as many kinetic energy from wind while minimizing the losses due to frictions and turbulence. This makes engineers tend to focus on the blade in various aspects.
Now, let's take a look to the explanation and application or technology concepts of the development of blade design for wind turbine. Firstly, for the concepts, it has many of concepts, but the three main of it is aerodynamics, length and shape, and control system. As for aerodynamics, it has blades on it that are designed to efficiently capture the wind energy. They typically have an airfoil shape similar to airplane wings optimized to generate lift and minimize drag. As we can see on the wind turbine, the blade has a design and shape that is like an airplane. So, with the aerodynamics shape of it, it could capture the wind energy so that it could be more powerful. As for length and shape, it has longer blades to capture more wind energy, but there's a balance with weight and structural integrity. Blade shape and twist are crucial to ensure optimal performance across a varying wind speeds. As for the control systems, pitch control adjusts the angle of the blades to optimize efficiency and prevent damage during high winds. Blade tips often move faster than the base, requiring careful engineering to manage aerodynamic forces. This is mean that control system and aerodynamics has relate with each other. So, the control system has to control the blade energy so that it could move faster than the base, but it has to be careful so that the blades are not damaged. And for the technological advances, it has computational fluid dynamics, which is CFD, and manufacturing techniques. And lastly, it has monitoring and maintenance. As we can see on the video below, that is how the wind blade is structured on wind turbine. As the application itself, it can be found on onshore and offshore wind farms, and then the scaling of sizes, which is important for the application of wind turbine because in my understanding, the bigger the wind turbines, the more power energy it could absorb. And then we have noise reduction of wind turbine. Lastly, environmental impact. Wind turbines are quite useful to the environment because it can prevent the produce of greenhouse gas. Now, let's move to the detailed explanation to the next slide.
Next, detailed explanation and application of technology concepts of the development of blades designed for wind turbine, such as structural design, materials, composite materials like fiberglass, carbon fiber, and explosive resin are commonly used for their high strength to weight ratio. Second, fatigue resistant. Blades are subject to cyclic loading and must be designed to resist fatigue over their operational life. Third, load bearing. Blades must withstand various loads, including aerodynamic, gravitational, and inertial force. Fluid element analysis is often used to model and test this blade. Moreover, technology trends. First, smart blades, incorporating sensor and control system to monitor and adjust blade perform in real life. Second, advanced material. Research into new materials that offer better performance and durability such as carbon nanotube and biocomposite. Thirdly, modular blades. Developing blades that can be assembled in friction to facilitate transport and installation.
Some of the real-life examples that we have is the Vestas V164 9.5 megawatt. This blade has a rotor diameter of 164 meters with its rated capacity of 1.5 megawatt. Since the rotor diameter is massive, it has high output that is suitable for maximizing energy capture in offshore wind conditions. Another notable example is the LM107P blade. This blade is a typical two-blade configuration made by the LM Wind Power Company with the rotor diameter of approximately 214 meters. The blade specifically designed for the turbines with even higher power outputs, leveraging its size to capture more wind energy effectively. Last but not least, we have the Siemens Gamesa B75, where it is at 75 meters at length, resulting in a rotor diameter suitable for turbines in the mid to large range. This makes it balance in between size and efficiency to cater both onshore and offshore wind projects with varying wind conditions.
Next, we have potential benefits and also challenges. For benefits, we have 4 here. First is noise reduction. By reducing the noise pollution caused by wind turbines, advanced blade designs can help make them more acceptable in residential areas and environmentally sensitive places. Second is cost reductions. Since they use less turbines or smaller installation to produce the same amount of power, efficient blades can lower the total cost of energy generation. Third is technological innovation. Technological developments in material science, manufacturing processes, and control systems are fueled by research in blade design and have applications outside the wind energy sector. Lastly is increased efficiency. Better wind turbine aerodynamic efficiency can be achieved through improved blade designs, which will improve wind energy conversion to electrical output. For challenges, we have cost of development. For innovative blade designs, research and development expenses can be high, requiring large investments in testing facilities, computer power, and prototype manufacture. Second is environmental impact. There may be negative environmental effects from the manufacture and disposal of composite materials used in blades, including waste management problems and carbon emissions. Third is scale-up challenges. Transitioning from a prototype to large-scale production may provide difficulties with supply chain management, logistics, and manufacturing consistency. Last but not least is complexity. Robust blade design requires complex aerodynamic models and structure engineering to guarantee dependability and security in a range of operational scenarios.
Hi, I'm PHY380. I'm gonna discuss about future developments of wind turbine blade. There's 3 of them. First, individual pitch control (IPC), band twist coupling (BTC), and lastly, multi-rotor wind turbines. So first, for IPC, it is an active control system, and the circulation is circulation control. It has CBIT, advanced control, in combination with fast response rate. So whenever there's a imbalance in weather or wind, they will respond very quickly. And how it works is it delivers compressed air from special slots on the blade surface. The compressed air then adjusts the aerodynamic performance of the blade. And then there is an elliptical aerofoil on the outboard rotor blade, which the elliptical aerofoil is very low solidity, so it's very much lighter than regular wind turbine blade. And the purpose of this design is to control lift, drag, and adjust the aerodynamic performance of the blade. And for example, this is the wind blade that is developed by Kohana, and we can see the inlet control valves and the forward blowing slot on the blade. And second one is band twisting coupling, which is BTC. It is a passive load elevation system. It's not controlled by operators or any automatic system. It's passive. And the way it works is allow a twist of the blade during extreme weather, and whenever there's like a strong wind or current, the blades can fold together. The slat or flaps are connected with spring. The purpose of this design is to reduce the risk of damage for wind turbine on a harsh climate. And for example, we have here is segmental ultralight morphing rotor SUMR, and you can see from the picture that the blade slowly will fold up like this whenever there's strong current coming up. So the risk of the blade getting damaged is getting less. And the third one is multi-rotor wind turbines. And this is a bit unique and a little bit different than the usual wind turbine blade that we have seen. It is a large power system installed at a single site. It works in multiple rotor in one wind turbine. The purpose of this design is to improve efficiency and reduce loads on wind turbine. It also could reduce some electrical costs. Independent operation of each turbine maximizes total load reduction and lower production costs due to smaller rotors. So instead of the factory need to order a large blade, they can order a small one, which is much more cost effective. And this is the example of it is Vestas multi-rotor wind turbine, and there's like 4 blade in one turbine.
The development of wind turbine blades has evolved over the years due to better materials, designs, and manufacturing. Initially, the blades were simple and made from materials like wood or metal, limiting to the efficiency and durability. Now, wind turbines has used lightweight composites like fiberglass to improve its efficiency. Modern designs now are more aerodynamic to capture more wind with less losses. Therefore, ongoing research happened to enhance performance and sustainability to meet the growing global demand for renewable energy.
And that concludes our presentation. Thank you for your attention and participation. Bye-bye.